Well, I don't think I need to persuade anyone in this room about the fact that computational models have become an essential source of information to support infrastructure decisions. But equally, I suppose we all agree on the fact that model predictions, model outputs are conditional on a range of uncertainty assumptions about the current properties and drivers of the system, and then when we want to use models to look at long-term planning, also how these drivers and properties will evolve in the future. Perhaps some of you are familiar with this pyramid picture that was introduced a few years ago, talking about how uncertainty propagates through long modeling chain when we look at, for example, the impacts of climate change. For models to be trustworthy and effective for infrastructure resilience, we must, first of all, avoid spurious precision. There is here a cartoon from the Royal Statistical Society. We often use models to compare, perhaps in a bar plot, the performance of different options. But each one of those bars actually should be attached with a quantification of the precision with which that variable has been estimated. And if those bars are large, then what is like actually the trustworthiness of the estimate? Is it correct to make decisions based on that? And if the precision is larger than the difference between different options, then really, do we have a robust evidence to go for one rather than the other? And then once we have established what is the level of uncertainty in our model predictions, another important task is to look at where is it coming from. So what are the key sources? And this is important because it helps us understand what are the critical assumptions that might invalidate the model. And also because from a more practical perspective, it gives us a roadmap of what are the priorities, where do we start first if we want to increase that precision, where is it that we need to invest on getting better quality data or improving some of the assumptions of the model, and that will have the most of the impact on our results. And also, again, going back to when we use models to look into things that will happen in the very long term, that can help us to understand what are options, design options that perform maybe not optimally against any of the given scenarios, but sufficiently well across a range of those scenarios, given that we don't obviously know which one will ultimately happen. So our project is very much about one particular set of methodology that somehow enables us to begin to answer all of these questions. So to quantify how much uncertainty affects our model predictions, and to track where is that uncertainty coming from. And there are methodologies to do this. These methodologies are generic, so they are applicable to any model. So in this project, we are not going to focus on one particular sector or one particular model. Our ambition is to bring methodologies that can be used by all DAFNI users, whatever their area of research. Just a little bit of technical details for those who might be interested. Essentially, this is based on Monte Carlo simulations, so repeated executions of the model against different combination of the input that are uncertain. And then we have a set of statistical techniques to help us quantify, so answer the question of how much uncertainty is there in the model output. To attribute uncertainty, so look at which of the inputs that we have sampled from mostly contribute to that output uncertainty. So in general, what is the precision and scope of validity of the model? And equally, we can use the exact same of mathematical techniques instead to answer a very different questions. Once we have established the model is good enough, fit for purpose, we trust it to be a good representation of the system for our interests. So now we begin to swap like models and systems. So we run experiments on the model as if we were kind of running them on in virtual on the system, and we can begin to look at, okay, what are design options that we can go for that perform well enough across a large range of variability of the inputs. Or even we can determine threshold values in those inputs, those tipping points where the system behavior begins to cross critical thresholds, or the other way around, tipping points that maintain the system within a good enough performance. So the idea in this project over the next 18 months, we want to essentially set the foundations to include this methodology into DAFNI, and also we want to begin to develop some pilot applications that will enable us to demonstrate to DAFNI user the value of this type of analysis. And from the implementation point of view, the perhaps most challenging bit, which is to run Monte Carlo simulations, should be already possible because there are functionalities within DAFNI that allows that. About the second step, those statistical analysis of input and output, we can rely on a lot of packages that do that. Well, I mentioned the one that I have developed because it's the ones I've been working on for a few years, but obviously there are others that can also be considered and we will consider. And in practical terms, the way we see the project working is we will develop a set of DAFNI workflows that will showcase in very practical terms how you apply these techniques to a proof of concept model. To begin with, I think we will look at the water and energy sectors, and then a big component of the project is training and dissemination. The good thing of developing pilot applications is that they become in themselves hands-on materials for training that we want to run, deliver during the project, but they will remain beyond the duration of the project. And then we want to work with the DAFNI development team and think about, okay, if this approach, if we wanted to scale this up then and apply it not to proof of principle models, but to real models with all their complexities, what is missing in the platform, what is it that needs to be upgraded and developed further to make this a viable options across different sectors. It's a team of 4 people between Bristol and Newcastle. Saskia is here if you want to talk to her, and then we have Hannah Bloomfield that brings in expertise in energy systems, and Gemma Coxon that brings in expertise in water systems. We are planning to work closely also with model users from the Environment Agency and National Grid to begin with, to look at also how they will benefit from having this kind of information on top of the point predictions. So long term, what we want to achieve really is contribute to enable and promote best practices for, someone mentioned it, I think Richard mentioned it, responsible modeling just before. So I think it's good we are all on the same page. And this is, well, an inspiring paper that came out a few years ago on Nature about, also how we ensure that models really serve society. And they mention, obviously, the importance of consideration of uncertainty, model uncertainties in this. And I'll be around. Here is my email address. This is really a project that is not focusing on one particular area. So if you have ideas, want to collaborate, want to think about how this type of techniques would work in your field, how they might use it, you want to provide case studies for our project, that's brilliant. We are very happy to discuss more.